All right, so welcome to these set of notes. What we're going to be talking about today are geometric sequences and series. Geometric is a little different than arithmetic. Remember that arithmetic are common patterns where we're adding a common difference. Uh, if we wanted to subtract, our common difference would be negative. For geometric, we're going to be multiplying by a common ratio. So this common ratio here is going to be either a whole number if we're multiplying, or if we're going to be dividing, that common ratio is going to be a fraction. So we have some new formulas for this. So we have a sub n equals a sub 1 times r to the n minus 1. It's going to be very helpful if your r is usually in parentheses. It's going to be very helpful when r is negative or when r is a fraction. If we want to figure out the ratio of something, we just kind of divide the second term by this first or the third by the second. So it's always like the next term divided by the previous one. And then we kind of have that same kind of formula that we talk with arithmetic, that I like to write it in a different format, where I'm going to put a sub n equals a sub k times r to the n minus k power. This kind of helps. This is almost like our difference formula that we had in the previous notes. This is going to be a lot helpful when we have like two random terms in a sequence and we need to either figure out the ratio or something like that. So keep that in mind for these notes. So the first couple of problems, what we're going to do is we're going to figure out, are these patterns arithmetic, geometric, or neither? So let's look at this first one. If we look at this, 2 to 4, we add 2. 4 to 6, we add 2. 6 to 8, we add 2. And 8 to 10, we add 2. So that would make this a arithmetic. Change my pen color here. Okay, so it's going to be arithmetic, where our common difference is positive 2. What about this next one here? Well, 2 to 4, I could add 2, but then 4 to 8 is not add 2. Well, then what about if I multiply by 2? Well, yeah, that works. 4 times 2, 8 times 2, 16 times 2. Sweet. So this is a geometric sequence where our common ratio is 2. So be kind of are very straightforward with these. If it's arithmetic, please put d equals, geometric r equals. It's a little thing that it's just going to be helpful later on.
All right, this next question has some logs in it. Is there a pattern here? Well, if you notice, inside of each of the arguments, what we are doing is we're adding a 0 to it. Or, if you kind of think about it, well, we have log of 10, and log of 10 squared is 100, log of 10 cubed is 1,000. So then this ends up being log of 10 to the 1 power. Well, remember that the default base for logarithms is 10. So each of these are base 10. And if you have the log base and the base of an exponent to be the exponent inside the logarithm, the argument, if those bases are the same, then your exponent is your answer. So each of these just simplify to 1, 2, and 3, and so on and so forth. So what's the pattern here? We're adding 1 each time to 1, 2 to get 3. So this is an arithmetic sequence where your common difference is nearly just 1. Well, what about this next one? We have natural log of 1, natural log of 2, natural log of 3, and natural log of 4, which, yes, there's a pattern. You're just adding 1 to each of the arguments. However, mathematically, there is nothing that we could add, subtract, multiply, or even divide to just increase the argument by 1. So this is neither.
So again, we're still saying with the same directions, is this arithmetic or geometric, or neither? Well, let's look at D. Does D look a little familiar here? Well, it should. This kind of looks like our arithmetic formula, where we have a sub n, or a sub 1 plus n minus 1 times d, where it looks a little different. But if I were to simplify this, distribute the negative 2 and combine like terms, I end up getting 8 minus 2n, which should look like a linear function, which means that this is going to be arithmetic. So what you can do is you can go through and plug in 1, 2, 3, 4, and 5, and you end up getting 6, 4, 2, 0, and negative 2. which are the first 5 terms of our sequence, which they asked us to write down. So looking at this, we can see that our pattern is subtracting 2 or adding a -2. So this is going to be an arithmetic sequence where our common difference is -2. So again, if we're subtracting, our common difference is going to be negative. Let's look at E here. We go 27 and -18 to +12. Seeing that difference in signs should automatically tell you that we're going to be multiplying by something, because that's the only way we can change signs in a sequence, is by multiplying by a common ratio that's going to be negative. So this is going to be geometric, and a good way to figure out what our common ratio is we can take the second term and divide it by the first, and we end up figuring out that that's -2/3. If you want to be very safe about this, maybe do the third term divided by the second term and see if it gives you the same common ratio, which is -2/3. So this is a geometric sequence where our common ratio is -2/3. So notice that our numbers are decreasing, and notice that our signs are changing. So that means that our common ratio is going to be a fraction, and it's going to be negative. So this next question here asks us to write the first 5 terms of the geometric sequence where a sub 1 is 1 and r is x/2. So the first term they already gave us was 1. So what I'm just going to be doing is multiplying by x/2 each time. So 1 times x/2 is x/2. If I multiply x/2 by x/2, well, x times x is x squared. 2 times 2 is 4. Then we multiply the top by x, get x cubed, multiply 4 by 2, and get 8. And then we do the same thing for the last term here. So that's 5 terms. We could write this as in a formula where if you want to, you can say like, oh, a sub n equals 1 times this common ratio to the n minus 1 power, which we don't really need this 1 here, but it is kind of helpful when you're writing the formula, so you remember like, oh, it's the first term times this. And again, notice that I'm putting that fraction in parentheses because both of these need to be raised to that power. All right, what about this problem here? Find the 9th term given a sub 1 equals 3 and r equals 2, root 2. Well, I could go through the pattern 3 times root 2 times root 2 times root 2 each time and try to figure out what the 9th term is. Or I can write a formula. So since we're talking about this common ratio, we have that formula a sub n equals a sub 1, which in this case is 3, times our common ratio. Notice that I'm putting it in parentheses to the n minus 1 power. Well, what's nice about this explicit formula is I can figure out what the 9th term is by plugging in 9 into my formula. Well, then what I'm going to do is I'm going to simplify this. And to make my math a little bit easier, in Algebra 2, you talked about roots being actual exponents. The square root of 2 can be rewritten as 2 to the 1/2 power. Cube roots are to the 1/3, fourth root to the 1/4, and so on and so forth. Now, why does that help me out here? Well, if I do 9 minus 1, I get 8. So if I simplify this, a power to a power is multiplying. So 8 times 1/2 is to the 4th, and this should be 3, not 2. And it's going to be helpful to know powers of 2's, at least up to like 6 or 7, something like that. Just write them down and kind of practice them. To the 4th is always the easiest one I remember because it's the same thing as 4 squared. It's 16. So 3 times 16 ends up being 48. So again, with a lot of these sequences and series, we have formulas. Use them. Don't start off with 3 and then multiply by root 2 and then multiply that by root 2 and then multiply. That just takes forever. Use a formula. It's going to be more helpful and you get a quicker answer.
All right, so this next problem, again, we're on our geometric sequence notes. So how do we find the 12th term given these 2 terms, the 3rd term and the 7th term? Well, since this is geometric, what I'm going to do, and I have 2 random ones, not the first term, I'm going to do the a sub n formula equals a sub k times r to the n minus k power. So the only thing I'm doing is that instead of 1, like a sub 1 and minus 1, I'm using k. because then I'm able to plug in, well, it doesn't matter which one which is, but I'm going to use the bigger term on the left-hand side and the smaller term on the right. You end up kind of getting the exact same thing no matter what. N is 7 and or K is 3. Well, they told us the seventh term is 256 over 243. They told us the third term is 16 thirds. And of course, we can do 7 minus 4, or 3 is 4. So in order for us to solve for r, we need to get rid of the 16 thirds. So I'm going to multiply both sides by 13 sixteenths. Might have said 6 there, but I apologize. And then we need to simplify that. Well, what if we do not give you a calculator for this question? How do I do this without a calculator? Well, 3 cannot be simplified any further, so I'm going to leave that as 3 to the 1. 16 is 4 squared, or 2 to the 4th, and you'll see why I'm going to use 4 or 2 here. And then 256 should be something that you kind of commit to memory. My benchmark is 2 to the 6 is 64. So if you double that, you get 128. If you double that, you get 256, just like, 2048. So you have 2 to the 8th over 243. Well, my benchmark with base 3 is 3 to the 4th. That's 81. If you multiply 81 by 3, you get 243. So that means that 3 to the 5th is the same thing as 243. Well, if we apply our exponent laws here, and I kind of move over here to this side because I ran out of room. If you are dividing like bases, like the 2 to the 8th and the 2 to the 4th, you subtract their exponents and you're left with 2 to the 4th. The same thing happens with the denominator, or the threes, base threes. If you have 3 to the 1 and 3 to the 5th, you're left with 3 to the 4th on the denominator. Well, if we're doing r to the 4th, I'm going to 4th root both sides, which is an even root, which means that we're going to get plus or minus 2/3, because the 4th root kind of cancels off with the 2 to the 4th and 3 to the 4th. So you're just left with plus or minus 2/3. What did they ask for? Well, they asked for the 12th term, not the ratio. So what I need to do is go back to my equation and plug it in. So I'm going to use that a sub n equals a sub k times r to the n minus k power. But instead of substituting in n, I'm going to leave it as n. So I'm going to leave it as a sub n equals the third term times r to the n minus 3, which they told us what n is. They told us it's 12. Then the third term is 16 thirds. And then we found out r is plus or minus 2/3, and then n minus 3. Oh, but n is 12, so I'm going to plug in 12 in there. So now it's just a point of simplifying this. Well, 16 is 2 to the 4th, and then 3. And then if we do 12 minus 3, that's 9. Well, if you take something that's positive or negative to the odd power, it's going to stay positive or negative. So I'm going to leave this as plus or minus 2 to the 9th over 3 to the 9th. And unlike the last step that we did, we are simplifying this by multiplying these two. So if you're multiplying a positive by a positive or negative, you're still going to get plus or minus. And if you're multiplying like bases, you add their exponents. So 2 to the 13th, and then this is 3 to the 1, so 3 to the 10th. And that would be the 12th term, depending on if your ratio is positive or negative, if your answer is positive or negative, but we'll just leave it like this. If you did have a calculator, you can probably put this into the calculator and get a more simplified fraction, but this is how you would do this without a calculator.
All right, so what about geometric series? That's when we're doing the sum of these geometric sequences. So we have two different formulas here because things happen when we're doing patterns that have a common ratio. So if you have a finite, that means you have a certain number of terms, like a partial sum, which we call it sometimes. We have a value of n, which tells us how many terms we're adding, and we have this kind of new formula. So we'll practice this a little bit. Then what ends up happening is we have another formula if it's an infinite series. That means the series keeps on going. With arithmetic sequences, like if you just think about whole numbers, you're adding like 1, 2, 3, 4. It just keeps getting bigger and bigger. So if our series is arithmetic and it's infinite, well, the sum's going to be infinite. That means we're just going to be adding numbers and numbers and numbers and getting bigger and bigger. Well, in geometrics, as long as my common ratio is less than 1, that means like it should be a fraction, not like 3/2 or 5/3 or anything like that, but somewhere like 1/2, 1/3, 2/3 even works. Just something that where if we do the absolute value, that is less than 1. Then we can actually figure out a sum. You can kind of Google out some ones, like if you kind of take a box and you cut it in half and a half and half and half, and you just keep on adding those halves, you end up getting a whole square if you infinitely add those up. But that's something you can Google on your own. But we're just going to talk about how we're going to use the formula here. So let's write this in sigma notation and do all that. So sigma notation, the way that we write that, you kind of remember, is we have that big sigma. So practice writing your sigma notation. That's a pretty good one for using this electronic tablet. And then we have a variable. And in this class, or most of the time, we're going to start off on 1. We might talk about later how we change this from 1 to whatever number we want. So remember that sigma notation, we start off plugging in the bottom number, and we plug in every integer that we keep going until we get to this top number. So we kind of need to figure out what our n is. What goes in over here is our formula. So that's going to be our a sub n. So 1 to -1/2 to +1/4. Oh, sign change. Numbers are decreasing, so it's going to be a common ratio where it's a fraction and it's going to be negative, and it's geometric. So since this is geometric, we're going to use that formula where it's a sub 1 times r to the n minus 1. So our a sub 1 is 1. Our r to the n minus 1, well, 1 to -1/2 to 1/4 is going to be -1/2 to the n minus 1. All right, so that will be my formula, and I really don't need that 1 in front, so I can just write that formula here, -1/2 to the n minus 1. Since we're alternating signs, you could honestly put that -1 to the n minus 1 or +1, whichever one that you like, or you can just leave the formula like this. So we need to figure out is what do we plug into n to get 1 over 10 to the 24ths. So I'm going to break this up a little bit, where I'm going to take the -1 and raise it to the n minus 1 power. And then I'm going to take this +2 and also raise it to the n minus 1. So I just kind of distributed that exponent. So we need to figure out what value of n do I plug in order to get 1 over 10^24. Well, the numerator doesn't help me out because -1 to the n minus 1 equals 1 can happen at any point when odd, or n is odd. Because if you plug in n is odd, you'll get an even, and -1 to an even power is always 1. So what we need to actually focus on is on the bottom in the numerator. That's going to help us the most. With n, whatever n comes out to, it hopefully should work out to the top. So 10 to the 1024 is actually 2 to the 10th power. And this is something that we did in Algebra 2, where if we have like bases, we can drop the base and just set the exponents equal to each other. So when we do that, we get n to the 11th, which, hey, 11 is odd. If I plug in 11 into here, I get -1 to the 10th power. And again, -1 to any even power will always be positive. So what is this n here? Well, it actually tells us where to stop on our sigma notation. So again, we start off on 1. We end up getting 1 in from this formula. If we plug in 2, you should get out -1/2. Plug in 3, get 1/4. Plug in 4, get -1/8. And if you keep on going, you end up plugging in 11 to get 1 over 1024. All right, so let's look at this next one. All right, so 1 over e squared plus 1 over e. So what's the pattern there? How would I go from here to here? Or here to here, or here to here? Well, this one's easy to kind of see. We multiply by e. Do I multiply by e here? I do. I multiply by e here as well. And since it keeps on going forever, this is a geometric series that's infinite. So we're going to use that same formula that we did just a little while ago on the last problem. So a sub 1, okay, is 1 over e squared. And then my common ratio is e. Do y'all know what e approximately is? Well, even though you don't know its exact decimal, you should know that it's 2.718, which should realize that, hey, that's bigger than 1. Even if I do the absolute value, it's going to be bigger than 1. So what I'm going to say is, since r is greater than 1, then the sum diverges. So we just talked about converges in that last problem. Diverges means that the sum goes to infinity. So that means that we're going to either have no sum or no solution. Read the directions on, which one you want to put. I usually like to just put that there is no sum.
All right. This next question here, what we're trying to do is we're going to try to use infinite geometric series in order to write 1.27 with the bar on top of it, which means it's repeating, goes on forever. So 1.27 with the bar on top of it can just be rewritten like this, and it just goes on forever. So how is this a geometric series? Well, that one out in front, I kind of added that to our notes because we kind of do this on our homework or quizzes or tests, and we want to make sure you know how to do this. The only geometric series that's happening is if you start with 0.27 and you add 0.0027 and you add 0.00027, hope that was 4 zeros, and you kind of keep going, 2, 3, 4, 5, 6, and it just goes on forever. But to get that 1 in front, we would add 1 to all of that. So this is how I could rewrite this as an expansion of adding a bunch of decimals. Well, the geometric series that's happening starts here and goes on forever to infinity that way. So that means this is our first term. And since I'm repeating 2 decimal places, our common ratio ends up being 1/100ths. So if I were to find the geometric sum of that, I would have the first term, 0.27. And yes, our ratio is, the absolute value of our ratio is between 0 and 1, so the sum does exist. So 1 minus r, which is 1/100ths. And then we try to simplify this. Well, 0.27, properly said, is 27/100ths. So 27 over 100. And then if I subtract 1 and 1/100ths, you end up getting 99 over 100. Which, since both the numerator and denominator are being divided by 100, you end up getting 27 over 99, which reduces down to 3/11ths. There are a couple of different ways of figuring out what is 27 as a repeated decimal as a fraction. This is the most straightforward and mathematical way of figuring out that if you type in 3/11ths into the calculator, you're going to get 0.272727 repeated forever until it rounds. Maybe it ends at 3 or 7, depending on your calculator. But remember, I'm not asking for just the repeated 27 decimal place like that's going on there. I'm adding 1 to that. So what you need to do is add 1 and 3/11ths, which 1 is the same thing as 11 over 11. So if you add 3/11ths to that, you end up getting 14/11ths. So if you were to type that into your calculator, you would end up getting 1.272727 repeated forever.
Evaluate this. How do we evaluate the sigma notation? Well, again, sigma notation is sum. So we're trying to find the sum of this. Now, what kind of series is this? Well, we have some first term times some ratio to a power. So anytime you have this exponent, this should actually signify that that's supposed to have been an arrow, geometric. So you have to be very careful with this because sometimes this formula has an exponent, and a lot of students think that this first term here is always the first, like whatever this coefficient is here, they think it's the first term. So I'm finding the sum of a geometric series. Now we have two formulas. We have infinite or we have finite. Is this infinite or finite? Well, this is actually finite. How do I know that? Well, it doesn't have an infinity symbol up here. That means that we're starting off plugging in 1, do 2, 3, 4, 5, and then 6. Stop at 6, and then you add all those up. Now, you could physically do that, or we have a formula. The formula could be rather helpful. So the formula for an for a finite geometric series is S sub n equals a sub 1 to the 1 minus r to the n power over 1 minus r. So I need to figure out what my first term is. So what's always going to be helpful, and again, I tell students to do this all the time and people just ignore me. What you're going to end up doing is always plugging in this bottom number in for n, because that's where we always start. So we do 30 to the negative 1/2 to the 0 power, which a lot of people think is still 0, which it's not. Anything to the 1 power or 0 power is 1. So our first term is 30. Wait a minute, isn't that just the a sub 1 in our formula? Yes, but not all the time. So just be very careful, plug it in every single time, and just be sure. Now, I could plug in 2 and get negative 15, plug in 3, get negative 15 over 2. Or you can easily find it. What's that base of the exponent? So our r is negative 1/2. Well, since this is finite, I need to know how many terms we have. And we talked about sigma notation. 6 doesn't tell you how many terms there is. It tells you where to stop. So anytime that this n is 1, then yes, that's 6's. But that's only if n equals 1 down here at the bottom. Sometimes it might start at 0. Sometimes it might start at 10. We don't know. But to find the number of terms, you always do the top minus the bottom plus 1 in order to figure out the number of terms, which again, in this case, is that top number. So let's plug this into the formula. So the finite sum of the 6 terms that we have in this sigma notation is the first term, 30, times 1 minus r. And again, whenever I plug in any kind of r, I always like to put it in parentheses. Even if it's like 3 or 2, I put it in parentheses because those parentheses matter. And when you're doing fractions like this and raising it to the 6th power, it actually does change a lot. So same thing down here, I'm going to put it in parentheses. So again, with the blend quiz, you most likely have a graphing calculator. You can actually type this all in there at the same time. If you want to simplify this parenthesis, you have to do the negative 1/2 to the 6th power first, then subtract that from 1. So we end up getting 63 over 64. 1 minus negative 1/2 ends up being 1 plus 1/2, which ends up being 3/2. And when you do all this and simplify your fraction, you end up getting 315 over 16, which most likely you're going to be asked for an exact answer, so leave it as that. It tells you to round, and you can round it. All right, here's another sigma notation. So again, we're going to find the sum of this, a partial sum, or in this case, we have infinite. So this is going to be an infinite sum. So since I have an exponent and it's infinite, this is a geometric series that's going to be infinite. So we're going to use a different formula. We're going to use a sub 1 over 1 minus r. Now, again, we have a very big stipulation with infinite sums that the absolute value of r has to be less than 1. Well, what I could do, I still need a sub 1, so is it negative 2? Well, let's see. Again, I always tell my students, let's plug it in. Just be very careful with this. So we're going to do negative 2 to the 1/3 to the n power, which we're going to start off with 1, which 1/3 to the 1 power is 1/3 times negative 2 is actually negative 2/3. Hey, the first term isn't negative 2. That doesn't always happen. So, be safe. A lot of students look at this and say, oh, the first term's negative 2, and then they get it wrong. Plug in your lowest value, which is always 1, and then you can go from there. Now, you could go in and plug in 2 and end up finding out that, that's negative 4/9, and so, or 2/9. But in this case, that base is always, that I don't use it a lot, but that base of the exponent is always our ratio. So our ratio is 1/3, which, hey, that's less than 1. That's good. That means that this sum is going to work. That means I'm going to take negative 2/3 and divide it by 1 minus 1/3. Well, 1 minus 1/3 ends up being 2/3. So when I just keep adding a bunch of these numbers together, it ends up converging to -1. Okay, so converges is going to be a good word to know. That means it gets to something. It might not always get to -1, but it's going to get very, 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 very close to what -1 is. So the more numbers that you add, the closer it converges to -1. So that's going to be our sum. Again, our sum might not always be -1, but it's going to get very, very close when we keep adding all these numbers together.